Good morning, all. I hope I'm able to hear you and you are able to hear me, right? Am I audible?
Good morning, Kushanji. Yes, you are audible.
Yeah. So we will start the session in 1 minute. And you can share your queries before we start the session so I can focus more on those parts while I'm conducting. So the agenda for today is to see the outcome of the software, which is ETABS or the SAP 2000, along with the modifiers that we discussed in the last session. So I hope the modifier aspect is clear that we took in the last session. Any queries there, you can ask now. And in the WhatsApp group, the discussion on the shells and plates is going on. You can also put in your query if it is there. Uh, so feedback from the last session, any query you have, you can ask right now.
Bhushanji, you are on mute, sir.
Yeah. Am I audible now?
Yes, perfect.
Okay. So we will go to the next session as there are no queries for now. And we'll start with the software that is ETABS and the safe CSI product softwares that are giving results for the bending moment and shear, and also the reinforcement for the slab design, considering thin shell. And when we go to safe, it gives the thick plate. Okay. So that is what we are going to see in the session today. So before going to the software, let me first have a discussion on the manual method for slab design as per IS 456 2000. I think everybody would have designed the slab considering the bending moment and the shear force as per IS 456. So anybody has compared the design of the slab in software versus 456 results? Anybody has done that? Okay. So first, let me open the IS code and first discuss on the concept of the IS code, basically. Okay. I hope my screen is visible to all.
Yes, Bhushan ji.
So IS 456 2000, it is very old code that we are referring since years for design of the slabs now. And so section 24, that is for the solid slab, continuous over the support, monolithic which supports slab spanning in two directions at right angles and loads on the supporting beams. So this is a important section that we have seen, and I don't think people have query in limited method of design that discusses on the collapse serviceability and durability. Three parts are there, and the local checks of the cracking, then your temperature. So all those reinforcement that has to be provided, the cover that has to be provided. So all those uh, partial safety factor, design value, characteristic loads that we consider for analysis and design remain the same in this particular case. Only thing is we are comparing the results of the software with the code formulas. So code uses the empirical formulas, whereas the software is using our FEM based routine. So first thing that we do for any element design as per the IS code is we calculate the effective length. Now for a continuous slab that is having, let's say, 4 or 5 spans, the effective length, if you have to calculate in X and Y direction, you calculate it center to center of the support, or you calculate it clear span plus effective depth on both sides. Okay, so that way, whatever is the higher side, that you will take the effective length, or in both directions, you will calculate it. So LX and LY, if it is a two-way slab. If it is a one-way slab, then you have to consider only in one direction. So the bending is always in the shorter direction. So you have to consider the shorter direction for the bending moment. Higher bending moment will be there. So the bottom reinforcement will be higher. Bottom reinforcement will be higher, and it will be at the lower position in that particular direction while you are detailing it. So this classification, that is the rib slabs. So these are the ribbed ones, or they are the waffle slab, and this is the solid slab. So two type of arrangements are there, and same you can see in the software also. One is the waffle or the rib slab, and the solid slab. Software is also giving two options for design. Now this is important, table number 12 and table number 13 if we are designing as per the IS code. And I can annote, and if you are able to see, let me know. Are you able to see the red line?
No.
Now can you see?
Yes.
Okay, let me redraw. So now you are able to see the red line I have drawn. Okay.
No, we can see just a dot, not a line.
Okay, only cursor you can see.
Yes.
I think you are not getting that access. Fine. So I'll close the annotation option. I hope you can see the black line that I have drawn.
G. Perfect.
So I'm drawing a continuous span of the slabs. Okay, so this is a three span, let's say two-way slab or a one-way slab, whatever the case may be, and its length maybe let's say 5 meters. Then it may be 6 meter, and this may be 7 meters. And dead load and live load is applied here. Dead load plus live load. This is a gravity case we are considering right now. So the total load that will come here would be self weight of the slab and the floor finish, right? So dead load will come as self weight of the slab plus the floor finish. Just hold on, some noise is coming in back. Okay, so this is the basically what it looks like at the ends. That is at the supports. There are negative moments, and at the center span there is a positive moment. Right? So uh, this is how we actually calculate the loading on that. Now, if we are calculating the bending moment, we require what is the WU, that is with factor of safety 1.5 times dead load plus live load if we are doing the gravity case, right? So this is how we calculate WU. From that we calculate the ultimate moment, which is uh, the factor. It may be alpha X or alpha Y based on the code 456 into WU into, so WU in the sense in kilonewton per meter square. That's why I'm writing like small WU. Sorry, and L effective the whole square. I hope whatever I have written is clear and you are able to follow up to this point.
Yes.
And these factors that we are seeing here, that is for the moment what we have to consider. One is the uh, table 12, in which you get the bending moment coefficient. Other is table 13, which is shear force coefficient. So M and B are to be calculated. Now at near the middle of the end span and at support next to the end support, at other interior support. So plus, so these are support moments and these are span moments, the basic difference between the two. The span moments are always in the center. They are always positive. So all values are positive. At the support, all values are negative. Negative bending moment will generate. And these plus 1 by 12 and plus 1 by 16 will be like in our particular case, this is the end span, so it will be plus 1 by 12. At interior, it will be plus 1 by 16. And again, it is plus 1 by 12. So this way, we take the bending moment coefficient for the center span, which is the positive moment calculation. Now you can do from here once you do the effective length calculation. So L effective is equals to center span plus effective depth on both sides you have to take. Okay. So effective depth of the beam that you have considered. Or it will be, sorry, not center to center. Either it is center to center span or it is a clear span plus T effective on both sides. So you have to calculate in both directions X and Y, okay, to use it for design for two-way slab. If it is one way, then you have to consider only the one way, one direction of L effective. So this is the basic procedure that we follow as per IS 456 2000 if we want to design it. And the major difference is we consider the slab as a membrane element as per IS 456 2000. Now, what happens when the slab becomes a membrane, as we had seen last time, that if it is a membrane element, then it has only axial forces. So, axial force is considered only. No flexure or shear is considered in the slab. So, what theory follows? Kirchhoff's classical shear, no, sorry, classical plate bending theory. So, this is what we actually do. So this is how we do it in the IS 456 2000. We calculate the bending moment and the shear values using table 12, table 13. What are the factors now required is the modification factor because L effective is dependent upon the modification factor. We calculate it and multiply it with the span so that based on the reinforcement you will get what modification factor to take. If the span is more than 5 meter, okay, you can see the two spans are more than 5 meter, then also you have to apply modification factor. And AST required upon provided, you can take one right now in the beginning, and once it is available you can recheck it how much difference is coming, and that this parameter is a critical parameter once we are designing as per IS 456 2000. And this is basically moment diagram you can create for your particular slab. So your analysis, your design, both are happening using the factors given in the IS code. So if I draw the bending moment diagram for this particular case, then it will be zero here. Then it will go like this, continuous support, and it will be zero here again. Okay. So this will be the bending moment, and your shear force diagram would be. So how will your shear force diagram look like? So how should I draw the shear force diagram on this for this continuous slab? So shear cannot be zero at support, right? So at each support there will be some shear. By that time, let me write the values of the code. At support at support next to the end support minus 1 by 10, at other interior support minus 1 by 12. So these we have written for the dead load, and 1 by 10, 1 by 12 is for the live load. So again, if we see for live load, it will be 1 by 10, and here it will be 1 by 12 positive for the interior supports. And again, 1 by 10. So at the mid span, this is for the dead load, this is for the live load. So this is how you will get the bending moment at the mid span. Now if I see at the end span 1 by 10, 1 by 12, 1 by 9 and 1 by 9 for the imposed load. 10, 12, 9, 9. So here the moment is 0, so it will not be there. And at the span next to the at support next to the end support, it is 1 by 10 here. So I will write is minus in the color minus 1 by 10. And what factor do I have to keep here? Is it 1 by 10 or 1 by 12? So at support next to the end support, at other interior support, two options are there. Now this is next to the end support, that's why I have kept minus 1 by 10. So what about this case? Whether it is 1 by minus 1 by 12 or minus 1 by 10, what factor should I keep here?
Again, 1 by 10.
So minus 1 by 10 because it is also near to the end support. So minus 1 by 10 and minus 1 by 10, this is for dead load. And for live load, it is minus 1.9 minus 1.9, 1 by 9. This is again, I will write as dead load and this is live load. So negative moments, positive moments for dead load, live load, you will calculate, and based on the effective length and the weight calculation, you will apply the factor alpha from these values. Okay, and another value is related to what type of, let's say we will see when to use table 12 and 13. So moment and shear coefficient for continuous beams. Okay, this is for the continuous beams we are considering. So whatever we have done is for the continuous beams, and these all moments apply to what continuous beams. Now, unless more exact values are done for beams of uniform cross section which support substantially uniform distributed loads, so for UDL type of loads over three or more span, so it has to be minimum three span and higher than that, which do not differ by more than 15%. So the difference in the span should not be more than 15%. So 5, 6, and 7. Okay, I have marked it here. So that should not be more than 15% difference in the continuous span of the longest one. The bending moment and shear forces used is in design may be obtained using the coefficients table 12 and 13 respectively. So for the beam moments, we will get continuous beams for three or more spans, UDL loads, you can get using table 12 and 13 of IS456 until more exact estimates are made. So what code has written, you can also make more exact estimate. So this line is critical that until we are not able to get more exact values, we should use these values. So when we are doing the manual calculation, then we have to follow these rigidly. Now, if I am using a FEM software and if the moment and shear values are changing, should I be taking or not? That would be the question because in the compliance, if you write that I have designed using IS 456 2000 or you are using the FEM software, out of the two, what case you will refer for submission of your design? That is very critical decision you have to take. For moments at supports where two unequal spans meet, or in case where the spans are not equally loaded, the average of the two values for the negative moment at the support may be taken for design. So, where coefficients given in table 12 are used for calculation of bending moment, redistribution shall not be permitted. So, important uh, constraint or restrictions are that you cannot do the redistribution of moment if you are following table 12 and 13. Generally, we don't do redistribution now, so we consider we design the beams accordingly. But previously, many people use redistribution method and try to do achieve it because the beam depth becomes very high. So in that case, redistribution was previously done. Now, in very limited cases, you can do that. You cannot apply redistribution method directly. So this is for the beams that we have seen. So these factors will be for the beams. Now uh, shear shear force coefficient. So these are bending moment coefficient. Now at the end support 0.4, 0.45 at support next to the end support, outer side and inner side. Okay, you can see for dead load it is slightly different 0.6, 0.55, and at other interior supports it is zero point 0.5 and zero point 0.6. So that factors you need to apply it again. So right, like I have written for bending moment, same the shear force coefficients will come into this. So here it will be zero point 0.4 at end support and 0.45 dead load, live load factors, and zero point 0.6 and 0.55. So here if we see for the shear it will be 0.55 here and it will be zero point 0.6 here. inside and outside. The same will apply on this side. It is same on the both sides. In dead load, and this is live load. Shear force coefficient. So this way we will get our analysis results from the values that have been mentioned for the beams. Now we will go towards the slab. So this is the modification factor that we use for beams. Okay, so same we are using for the slabs also. Now we come to the solid slab, that for two-way slabs of shorter span up to 3.5 meter with mild steel reinforcement, the span to overall depth ratio given below may generally be assumed to satisfy vertical deflection limits for loading up to 3 kilonewton per meter square. So now for two-way slabs of shorter span up to 3.5 meter with mild steel reinforcement, for high strength you multiply by zero point 0.8, but critically up to 3.5 meter. Now we generally are having spans of more than that in our design. Okay, so if it is a two-way slab and it is up to 3.5 meter, then these values hold good. Otherwise, these values don't hold good. So why I am specifying all these things, because it is very mandatory to do the compliance of the codes. So what IS456 has written versus what you are actually doing for your projects, all should be complied. Direct blind copy paste would not serve. Okay, so you should remember that what are the boundary limits in which the code can be applied, and if it is not within the code boundary, then how to do it. So that is the reason I am going through 456 2000 code. So for the slab spanning in two directions, the shorter of the two spans should be used for calculating the span to effective depth ratio. Okay, L by D ratio should be taken of the shorter span. Now simply supported slab and the continuous slab. So your uh, L by D ratio, it is 35 and 40. So if it is a continuous slab, we are having, so 40 multiplied by 0.8, we have to use it. So 8 by 10 would be your 4 into 8, 32. So our value will be 32. Now slabs that are continuous over the supports in one direction and continuous over the supports shall be designed according to the provisions applicable to continuous beams. So why I had showed you the beam table before, because for continuous slab and for one-way slab, okay, that are continuous over the one-way or two-way slab that are continuous over the supports, they are to be designed considering the factors given in the beam section, table 12 and table 13. Now slabs that are monolithic with supports. So bending moments in slabs except the flat slab constructed monolithically with the supports shall be calculated by taking such slabs either as continuous over supports and capable of free rotation, or as members of a continuous framework with the supports taking into account the stiffness of each support. If such supports are formed due to beams which justify fixity at the support of slab, then the effect on the supporting beam, such as the bending of the web in the transverse direction of the beam and torsion in the longitudinal direction of the beam, wherever applicable, shall be considered in the design of the beam. So it is clearly mentioned that whatever the forces that are transferred from the slab to the beam, if it is generating torsion, whether it is generating bending in the web, okay, so all should be considered for slabs that are monolithic with supports. Now continuous over the supports and monolithic with supports. So these are related to the end base. So end base where the span is ending, so your slab will be monolithic with the support, and in the interior the slab will be over the support. So two cases are represented by the IS code, and this way it has to be followed. So end span, mostly the beams are failing in torsion, as you see, and many people release that torsion just by itself, assuming there will be no torsion, or there are many things people do. It is clearly mentioned that whatever the forces are generated by the connecting of the slab with the beam, uh, which is monolithic with the support, it has to take that twist and it has to take that uh, bending in the web. Whatever is getting generated, all should be considered. Okay, so this is very critical. People don't follow properly this particular clause. For the purpose of calculation of moments in the slab in a monolithic structure, it will generally be sufficiently accurate to assume that members connected to the ends of each slabs are fixed in position and direction at the ends remote from their connections with the slabs. So, what is the meaning of this particular clause? What it actually means? So, can anybody explain this clause? For the purpose of calculation of moments in the slabs in a monolithic structure, it will generally be sufficiently accurate to assume that members connected to the ends of such slabs are fixed in position and direction at the ends remote from their connections with the slab. What they are saying that where the slab is getting connected with a beam, at that position we will take the beam as a fixed connection, and which is away from this joint, they are connected with the slab. Okay. So, fixity, if you assume that moment calculation will come into picture. If you release the moment, then the moment will not generate. So, when to release, which type of elements to release, when not to release is very critical. Otherwise, it will lead to cracking in the extreme load case, may not be in the routine case. So, that is very critical part. So, this is not of that critical thing. So this is important that slab spanning in two directions at right angles. Then we have annexure D, in which the coefficients are given, or it may be designed using any acceptable theory or by using the coefficients in annexure D. So what is this acceptable theory? That is very critical. There is one yield line theory, okay, by which you can design the slabs. For determining the bending moment in slabs spanning in two directions at right angles and carrying concentrated load, any acceptable method adopted by engineering charge may be adopted. So the most commonly used elastic methods are based on Pigott or Westergaard theory, and the most commonly used limit state of collapse method is based on Johansson's yield line theory. So elastic methods are Pigott or Westergaard theory that you should refer from any good textbook in detail, and most commonly used limit state of collapse, that is the ultimate capacity, that is Johansson's yield line theory. So that is how the analysis or the design of the slab has to be carried out. I hope I am reiterating 456, but there is a purpose to reiterate it again today. So I hope I am making some sense. Otherwise, I can directly go to the software. So should I continue with 456 some more, or should we jump to the software?
It is good to refresh.
Okay. Okay. So now there is now distribution of the moment for two-way slab. If you see, this is how trapezoid and triangular load distribution happens. And any standard textbook will have this formula for load distribution. And once you are able to calculate that load, so load transfer from the slab to the beam. This is how it is done. So in the previous, what I had written in my this white screen, that it was uh, some W into L square into the alpha x or alpha y. That is the moment generated on the beam. Now, as per this diagram, if you see, then there is some distribution in trapezoidal and triangular manner in the two-way slab, not in one-way slab. In two-way slab, this is how it will distribute the load. So you calculate that load, and then you can use it for design. Okay. So this is uh, how the WU to be calculated for the two-way slabs. So trapezoid was and triangular. The intensity is the same. Only thing is distribution of force in two different directions is separate. So that is for the slabs, solid slabs. So minimum reinforced area of the tension reinforcement shall not be less than given in the following or side faces or the beams. But you can see it here that redistribution reinforcement, if it is FE415 and percentage redistribution to or from the section considered. So that way it is to be considered, and temperature steel has to be provided at 300 center to center, not exceeding 300 spacing, side face reinforcement or your reinforcement for the tension, the temperature. I think this is for the flat slabs, and all are clear with this theory that column strip and the middle strip is to be taken. Now 0.25 of L1 or 0.25 of the L2, that is on both sides of the column. You have to consider a strip which is 0.25 times. Uh, so column strip means a design strip having a width of 0.25 L2 but not greater than 0.25 L1, where L1 is the span in the direction moments are being determined, measured center to center of supports, and L2 is the span transfers to L1, measured center to center of the support. And middle strip is the strip between the two column strips. And what is called a panel? Panel means the part of the slab bounded on each of its four sides by the center line of a column or center line of adjacent span. So between the center line, it is a panel. This panel is divided into column strip and the middle strip for analysis. So again, if we are going, the minimum thickness of the flat slab should be 125 mm as per the code, and the L by D effective of the previous section that we saw is also governing here. Now, this is a column drop. If the shear capacity is less and the slab thickness is not able to take the shear, then you have to provide the column drop. Now, what should be the size of the column drop? Can anybody explain what is a drop and what is a column head, and in which cases we should provide a drop and a head?
Drop is generally for punching shear.
Punching shear and column head. So again, if the drop is not able to satisfy the load of the shear, then we provide a column head also. Okay, so it will increase the shear resistance at the joint
Yes.
of the column and the slab. So so the length in each direction. So drops are always rectangular in plan and have a length in each direction not less than one third of the panel length in that direction. It should not be less than L by 3. For exterior panels with the width of the drops at right angles to the non-continuous edge and measured from center line of the column shall equal to one half the width of the drop for interior panels. So whatever L by 3 you have considered on the interior, the half of that has to be provided on the exterior uh, drop panels at the edges, perimeter of the building. So there are two methods of analysis in this. It shall be permissible to design the slab system by one of the following methods: direct design method and equivalent frame method. So this direct design method, equivalent frame method, you can get it in the textbooks. I think you would have gone through the both the methods. If not, then kindly go through it. And if you have some query, you can ask me on the direct design method and the equivalent frame method. In case the applicable limitations given in this shall be met, in each case, the applicable limitations given in 31.4 and 31.5 shall be met. So method of analysis, it should, whatever it is mentioned below, it should be matching those limitations. So bending moments in panels with marginal beams or walls. So where the slab is supported by a marginal beam with a depth greater than 1.5 the thickness of the slab or by a wall, then in that case, total load to be carried by the beam or the wall should comprise those loads directly on the wall or the beam plus a uniformly distributed load equal to one quarter of the load on the slab. So whatever the load is there, divided by 4 plus whatever the load is coming on the beam or the wall has to be carried by a beam or a wall that is having a thickness greater than 1.5 times the thickness of the slab if the beam or the wall is provided. Now, bending moment on the half column strip adjacent to the beam or the wall shall be one quarter of the bending moment for the first interior column strip. So, the bending moment on the half column strip adjacent to the beam. So, whatever is near to the beam, the column for that. Okay. So, half column strip uh, to the beam or the wall shall be one quarter of the bending moment for the first interior column strip. So at the ends, if the beam is provided like perimeter beam is there, so in that particular case, what you have to do for that column that is connecting with the beam, half column strip on that particular what loading to be taken L by 4. Sorry, bending moment by 4. So one quarter of the bending moment for the first interior column strip. So that divided by 4 has to be taken by that particular column. and the load taken by the beam or the wall, load taken by the column. So two criteria are there. Whenever a beam is provided along with the panels, mainly at the perimeter, this you have to consider for the beam and for the column that is connected to beam. So that loading will go on. So this load divided by 4 for the beam and the wall, and moment divided by 4 for the columns. That has to be considered. So transfer of bending moment to columns when the unbalanced gravity load, wind, earthquake, or other lateral loads called transfer of bending moment between slab and column, the flexural stresses shall be investigated using a function alpha of the moment given by 1 upon 1 plus 2 by 3 root of a1 upon a2 overall dimension of critical section for shear, overall dimension of critical section of shear transfers to the direction of which moment is acting on the other direction. So in direction of the moment, other to the direction of the moment, uh, that dimension ratio has to be there. 2 by 3 plus 1 divided by this value will give you alpha, and a slab width between lines that are 1 and 1/2 slab or drop panel thickness 1 by 5d each side of the column or capital may be considered effective, d being the size of the column. So a slab width between lines that are 1 and 1/2 slab or drop panel thickness. What does it mean? A slab width between lines that are 1 and 1/2 slab. So what it is actually representing? A slab width between lines that are 1 and 1/2 slab. So on each side of the column.
So this could be the middle strips or the side strips.
So it is talking about the slab width, first of all, not the length. Okay. So now how much width is to be considered? So a slab width between lines. So what type of lines it is saying? That are 1 and 1/2 slab or drop panel thickness. That is 1.5 times the D. So width will be 1.5 times the D if the drop panel is there. And either it is a which drop panel, then 1.5 D. If it is not a drop panel, only a slab and the column, then you have to consider one full width of the slab. That is along the width of the particular thing. So column is at the center line. So both sides of the column center line, you have to consider the width of the slab for loading, right? So it is talking about that. So how much width to consider for the slab above the column, which has a drop or does not have a drop. So concentration of reinforcement over column head by closer spacing or additional reinforcement may be used to resist the moment on this section. So that is the detailing part that has to be taken into consideration. So direct design methods, so slab system designed by direct method shall fulfill the following conditions. There shall be minimum 3 continuous span. The panel shall be rectangular. The ratio of the longer span to shorter span shall not be greater than 2. So it is, let's say, uh, if it is not greater than 2, then it is two-way slab, right? So it has always been the two-way direction. It shall be permissible to offset columns to a maximum of 10% of the span. So offsetting on the column that is away from the center, so CG of the placement of the element above the column, only 10% offset is allowed. The successive span lengths in each direction shall not differ by more than one-third of the longer span. So same as that we had seen, the span should not be more than one-third the longer span. In this case, the method is applicable. The end span shall be shorter but not longer than the interior spans. So end spans have to be equal to or shorter than the interior span. It should not be more than the interior span. So what I had shown you in the diagram, it was 5, 6, 7 meter. So end span cannot be more than the interior span. So this criteria has been set. The design live load shall not exceed so the design load live load shall not exceed 3 times the design dead load. So applicable requirement is live load should not exceed 3 times the dead load. Okay. So this is also very critical parameter to evaluate. So these results will can be useful to you only and only if you take care of all these limitations that are given in the code, and those parameters that are mentioned, factors that are mentioned are applicable within that boundary. Once you go beyond that boundary, then this code is not compliant. And if you are not using the given clauses, then also you are not compliant. Okay. In the cases in which it is applicable, you should take out the worst case, and in which case it is not applicable, you should carry out the analysis routine or the design routine separately. This is what is mentioned by all the requirements given in the code. So W L square by 8 is the bending moment, positive bending moment at the span. So in the direct design method, the total design moment for a span shall be estimated for a strip bounded laterally by the center line of the panel on each side of center line of the supports. So center to center, we are considering the span. So face to face of the column, this is Ln. We are considering Ln for the bending moment, which should be not less than 0.65 of L1. Okay. So L1 is the direction in which moment is calculated. L2 is the other direction perpendicular to the moment in which you are calculating the bending moment. So L1, L2, and Ln, three spans have been mentioned here. So in an interior span, the total design moment shall be distributed in the following proportion: negative design moment 0.65 and positive design moment 0.35. So, so negative design moment shall be located at the face of the rectangular supports, circular supports being treated as square supports having the same area. So at the face, you are considering the negative moment. Okay. Now in a interior span, the total design moment shall be distributed in the following proportion. So you calculate the total moment and distribute 0.65 on the support and 0.35 in the span. So direct proportioning has been done. So whatever the total design moment you have estimated for the interior span, that span moment 0.65 will go on the support, 0.35 will be in the center span. So that moment becomes a design moment for center span in the bottom reinforcement. The negative reinforcement that is on the top side near the supports will be 0.65 of the total design moment. So this way you have to distribute the moment that is calculated for the interior spans. And in an end span, the total design moment mu shall be distributed in the following proportion. So for end span, it is critical: interior negative design moment and positive design moment. So interior means on the inner face and outer face. So 0.75 minus 0.1 upon 1 plus 1 upon alpha c. So you will get a factor. Positive design moment factor would be 0.63 minus 0.28, 1 plus 1 upon alpha c. And exterior negative design moment on exterior face 0.65, 1 plus 1 upon alpha c. So you see interior face, it is 0.75. Here it is 0.65. So it is less on the exterior side, more on the interior side. Now alpha c is what? Flexural stiffness of the exterior columns to the flexural stiffness of the slab at a joint taken in the direction moments are being considered. So sigma AC upon sig upon Ks. Okay, this is the slab. The flexural stiffness of the slab Ei. Okay, and sum of the flexural stiffness of the columns meeting at the joint. So if there are one joint is there, so let's say one interior span is there. So how will you calculate sigma c? Why it is taken as sigma? Sum of the flexural stiffness of the columns meeting at the joint. If there is one joint, there will be only one column. So how it is saying the number of columns meeting at the joint? What is this sigma c basically? So above the floor and below the floor, the column stiffness you have to consider, and this is the flexural stiffness of the slab. If the beam is provided, that stiffness also has to be considered. It shall be permissible to modify these design moments by up to 10%, so long as the total design moment for the panel in the direction considered is not less than determined. So this is the 10% variation based on the size of the panel. So this is the column moment that is above and below the slab. As a joint action, both columns will resist this moment. Okay, so it has to be designed for that. Dead load, live load has been considered in this formula. L2 and WD dash are for the shorter span, and WD and WL are for the span being considered on longer span. So longer and shorter span, both values are there that are considered for calculating the bending moment on the column. So live load to dead load ratio also has been mentioned that when the ratio of live load to dead load exceeds 0.5, so like if it is 6 kilonewton, 5 kilonewton meters per is the live load and your dead load is less than that, and it is exceeding zero point 0.5 means let's say it is 1 equal, both are equal, dead load and live load. So in that particular case, the sum of the flexural stiffness of the column above and below the slab shall be such that alpha c is not less than appropriate minimum value alpha c minimum specified in table 17. So you have to follow this particular ratio, imposed load upon dead load ratio. First, you have to calculate. Based on that, L2 upon L1 ratio you will make, that is span of the your flat slab in two directions, L1 upon L2. What is the ratio for that? And based on that, you will get the alpha C minimum. This alpha C minimum you have to put, and you know the stiffness of the slab. And from that, you calculate the stiffness of the column required. So required stiffness of the column has to be estimated if live load upon dead load ratio is exceeding zero point 0.5. Okay. So many checks you have to do even after doing the analysis and design in the computer. If the sum of the flexural stiffness of the column sigma Kc does not satisfy, the positive design moment for the panel shall be multiplied by the coefficient beta s given by the following equation. So now if you are not able to control the stiffness of the column, then you have to add this factor beta s, which is dependent upon dead load, live load, and alpha c upon alpha minimum. So what is the current alpha c? What is the current alpha c expected? That ratio beta s you have to apply the moment into this factor. Okay. So this was on direct design method. Now, when we go to equivalent frame method, the bending moment and shear forces may be determined by an analysis of the structure as a continuous frame, and the following assumptions may be made. So bending moment, shear forces may be determined by an analysis of a structure as a continuous frame. So what is the meaning of continuous frame? That stiffness matrix will consider slab, beam, and you will do equivalent framing as a frame you will consider, like we do it for the moment resisting frames. Same way the frame system will be there, and you will estimate the bending moment and shear forces considering that. So these flat slabs also can be modeled as frames using the approximate method. So if we have to evaluate better, understand better, you should do the approximate method of analysis for the flat slabs, which is given in one of the books, in which you consider the effective width of the slab over the columns. That way, the analysis problems problem reduces, and you can solve it faster, and it will give more accurate results as well. So previously, when there were no good softwares, it was considered as a equivalent frame. You can manually calculate the stiffnesses and analyze the structure. So that way, you can also manually check the results using the approximate methods. So all these parameters, rest of the things you can refer, and negative, positive design moments are again to be estimated, like we do it for the direct design method. Now, the shear in flat slab is critical. The critical section for shear should be at a distance d by 2 from the periphery of the column oblique capital oblique drop panel. So wherever there is a column, then d by 2 from there, wherever the capital ends, d by 2 from there, wherever the drop panel ends, d by 2 from there, effective thickness of the slab. You have to consider that region to estimate the shear. So figure 14, if we see mm, effect of free edges. Now this is your column and this is the free edge. So it is where it is terminating at the perimeter. Okay. And here also there is a free edge at the perimeter. You can see this is the consideration. So d by 2 here you have to consider. Now this is your critical section marked like this dotted line. So d by 2 on all sides, on two sides. Here it is on three sides. So why uh, here also three sides has been shown d by 2. And all round in the interior spans. For circle also it is a diameter of d by 2 higher. This way you have to consider for the shear when opening in flat slabs are located at a distance less than 10 times the thickness of the slab from a concentrated reaction, or where the openings are located within the column strip, the critical section specified in 31.6.1 shall be modified so that part of the periphery of the critical section which is enclosed by radial projection of the openings, the centroid of the reaction area, shall be considered ineffective and opening shall not encroach upon column head. See figure 15. So your openings, where to keep it, it should not encroach your strip. Okay. So column strip is away, that is okay. Now here also there is the opening, there is a large opening, and here it is a column critical region. So it should be outside column critical region. So whatever the opening are there, it should not be within the column strip. So permissible shear stress is Ks into tau c for the flat slab. Ks and tau c are the same that we do it for footings as well. So rest all is part of detailing and all other requirements. Openings, where to keep, where not to keep, how to consider. The last part left out is the annexure. So restrained slabs, slabs spanning in two direction when the corners of a slab are prevented from lifting. So those are called the restrained slabs. The slab may be designed according to this equation: alpha x w lx square, alpha y w lx square. Lx is the shorter direction, effective length. So there is a slab is always divided in middle strip and the edge strip. So edge strip will be Lx by let, let me see. Think what I remember it was Lx and Ly by 8, but again I have to check this value, but that has to be seen. And 3 by 4 and 2 by 4 is 1 by 4. Yeah, it is Ly by 8 and Ly by 8, Lx by 8, Lx by 8. So 3/4 middle strip, okay, and your 1/4 is your edge strip. Now 1/4 divided by 2 will be 1 by 8 Ly and 1 by 8 Ly on two sides. So this is how the longer direction, shorter direction, middle strip and end strips are to be formed. And the bonding moment is to be calculated for both the cases, and your uh, uh, analysis will give you now after that moment you will get mu by bd square, and from SP16 you will get the reinforcement, top reinforcement and bottom reinforcement. Now these are various conditions. Rectangular panels supported on four sides with provision for torsion at corners. So interior panels, one short edge continuous, one long edge discontinuous. All those 9 criterias have been mentioned. What criteria is suitable to you? From that you have to consider, but we'll see where it is written, table 26. So this is for table 27. Table 26. For simply supported, we have to refer this table 27. However, for this rectangular panel supported on four sides, which are supported on all four sides, which are not simply supported, you have to follow this table 26 for calculating the factors for the moments alpha x and alpha y, which I don't think anywhere it is mentioned. So 25, 27, 26 table number, nowhere I can see it. Okay. So that was on IS456 that all these criterias have been covered for beams. So two things are to be designed in this. One is the slab and the beams. And for flat slab, it is the slabs, beams, and the columns. All these are very uh, detailed manner. The assumptions are given in the methods of analysis and design followed by IS 456. If you want to comply 456, you have to follow all these constraints. And whatever is beyond this code clauses, you have to consider it in analysis and you have to design and prove it and check for the worst case. Okay. So we will now go to the software part, but I'll take a 3-4 minutes break before we go to the software so that you can also go through the code I we have seen right now. So if you have some more queries, you can ask. So we will get back at 12:30 in 4 minutes. Hello, I hope again I'm audible to you. Akbar, am I audible? Hello, Dheeraj, I'm audible.
Yes, Bhushanji.
Okay, so we will continue now with the software, the results of it, which has to be compared manually on your side. So the basis of calculation, the software module, this uh, clauses that I have covered, that has to be manually done and compared with the software to arrive at a better conclusion on the methods we are adopting for floor system design. Okay. So I open eTabs right now. Trying to make the same that I had drawn. So there are options called flat slab without the perimeter beam, then the flat slab with perimeter beam, then this is the ribbed slab, then two-way or the ribbed slab. So that way you will directly get this option. So right now I am taking the grid lines. So you can see this is not added. So material property already it has been mentioned here. M30 45415. You can update it later. And this is for the columns, or you can also not have columns. You can just directly provide the supports here. Okay, all these edges you can select. issue is there. So we'll first define the slabs. So it is a 150 slab that I am considering. It is M30 grade, and right now I'll take the membrane, and I will consider either as one way or two way, whatever I want it. Right now, considering two way, so 150 and I'll apply it here 150 So right now there are no beams modeled right now. So I'll add the beams also. Okay, so beams and slabs are modeled. I'll just take the supports. Or let me draw the model. Otherwise, the beam moments will not come into picture. I'll define the column as well.
Hello, am I audible?
Yes, Bhujan ji.
So due to some issue, the laptop got disconnected. Maybe some auto update was there. I'm again
No
starting
problem.
the laptop. Hold on for
Sure,
two,
no
three
problem.
minutes. So by that time, can anybody tell that you have designed using the E-tabs, the slabs, and any other floor beams, all those things? So your feedback on that, your experience on that, and your validation on that.
Hi, Bhushan. Uh, I didn't use ETAP till now, but using manual or Excel sheet, we have designing slab.
Okay. Hope I am audible again and visible also.
Yeah, 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 yeah.
So your feedback by that time I open the software and again we have to model again that thing. So your take on the software that we are using for analysis and the design of the slabs, flat slabs. Uh, how is your experience in that? So anybody has validated the designs as per IS456 in software? That would be the question. Anybody?
Bhushan,
Yeah.
hi, Bhushan. I didn't design a flat slab till now, so this is
Okay.
like, but other slab we have done manual or using Excel site, Excel sheet. ETAP for me is new. So, like, sorry, but like, I don't have experience of this.
Yeah, no problem. So after this session, you can compare your Excel sheet with the same problem in this. So you can create a 3D model and you can do it manually from your Excel and from this. So one is you use the software as an analysis tool and you design the elements by Excel sheet, which we are mostly doing when we were using the STAD software. Okay, so we use STAD as an
Correct.
analysis tool. We don't use it as a design tool. We design in Excel sheets, that is columns, beams, slabs, walls, all be designed by our Excel sheets. Now, when we are going towards more on the finite element side, so the requirement has changed a bit, and in that particular way, whatever you are considering right now within the boundaries of the code, if it is not there, then you have to use the software for that particular purpose. So, like the backstay effect, if you want to consider model the flow for the backstay effect, then in that particular case, the location of the shears is critical. So you have to design for that. So you have to find that location and then design for it. So all those considerations where it is necessary, you can consider that way, and in optimization also. So if you want to reduce the beam depth is very high and you are not you are finding a solution to reduce the beam depth. That is what we are going to see right now in ETAP software, that how we can control the beam depth by considering it as a thin shell rather than a membrane. So in that particular case, it can also be useful to us. So I hope my screen is again visible. I have shared the screen.
Visible.
Let us consider two stories for now. So what is the benefit of the software is that you can also do the composite design in this particular thing which does not have valid Excel sheet. So in those particular cases, composite slabs, decks, you will
Hello, am I audible?
Yeah, audible.
Yeah, so again, the computer has some issue. It is getting switched off while I'm using eTabs. So I have to see that whether we'll be able to do the eTabs today or not. But I will separately put a video on eTabs results in my YouTube channel along with this session. So you can go through that video. So I don't think we'll be able to use eTabs today in my PC. Maybe I don't know what is the reason, but I'll upload the part in the video, take a recording of the video and share it in the YouTube channel. So basically, the exercise that is to be done is you design a slab using IS code, comply with the IS code, and then you design it in the software and you check for that compliance. All things are, which is the governing case, and based on that, you can do the next part of it. Like you use software only for analysis, or you use software for analysis and design, and in which cases you have to consider software for the design part for the slab. Okay. So analysis and design of the slab will change from software to your manual results. Okay. So that way the exercise has to be considered as completed. I hope I am clear. So Mr. Akbar, uh, I hope the software part I will cover in the video for eTabs to
Yeah,
follow for you. And the rest part you are doing already in the Excel sheet.
correct, correct.
And Dheeraj, you have any queries?
Yes, same actually. ETABS is new to me, so it's okay. We can follow you on your channel.
So I'll upload how to model, how to create the model, how to analyze it, how to design it. We will go step by step on that.
Sure, no
So
problem.
only part that whatever we do it in the software, that manual result has to be evaluated from your side. And if you have any query, you can ask me on that.
Sure.
Okay. So this recording plus the recording of the video, I will upload on my YouTube channel, and I will share it in the email also. So once that video is made, after that I'll share the recorded session for today.
Okay.
Okay, so my main intention was to cover the boundary limits, what code has put, what is a thin shell, what is a thick shell, what is a plate theory, what is shear deformation theory, and in which cases we have to use it, and which cases we have to evaluate the behavior of the slab system for design and analysis, and how to comply with the code. So that was the main intention of this webinar. That was 1 and 2.
Yeah.
Yes, sir. Yes.
So thank you for joining. For any queries you have, you can contact me on WhatsApp. You can call me, or you can put it in the group. I'll revert to that.
Thank you
Thank you,
for
Kushal.
organizing this. Really,
Thank
I'm
you
very
for
thank.
e-tabs part. I'll upload it. Once I'm able to do it, I'll share it with you.
Okay, sir. Okay. Thank you for organizing
Thank
all
you,
this.
Kushal. Thank you.
Thank you. Thank you. Yeah.